Hello, good morning, good afternoon, or good evening, everyone. Whenever you're watching this video, you're watching live. In my area, you would be in the um, mid afternoon. So today, I'd like to talk about two of the labs I usually do in Physics 20 Unit C, which is a circular motion energy lab. Circular motion one is a little bit more interesting, as you can see over here, and the energy one is a little bit more fidgety, but it's also quite interesting. So let's take a go over these two labs and see how it works. So the first one is a circular motion lab. It can be done fairly straightforward. It's basically I usually use a little plastic cylinder or or anything that can be used to hold a string and redirect string. Basically, act as a pulley, but not a full pulley because a full pulley the string might slip. Okay, that indeed actually contribute to a little bit to this as a source of error. Okay, usually use a little piece of plastic cylinder right here and have a string, and the string hangs with some mass that's adjustable. I just use washers. All right, and if the string acts as a pulley, okay, so the force of gravity. Okay, I gotta change color here. The force of gravity on the weight and the tension will of course be balanced out if when we spin, it keeps the height of the the mass unchanged. Okay, how to ensure that the height of the mass is unchanged? I usually clip little alligator clip here, and when I have students spin it, or I spin it myself, I make sure I try to. It's a little bit estimation that the alligator height does not change. Once again, of course, it's eyeballed, so that can be assumed there's a little bit of uncertainty, which you can account for in the measurement. The good thing about keeping this height unchanged, that also means this radius will be fixed. So throughout this experiment, the radius should be fixed for all trials. So the alligator clip basically all at the same height. Now, that of course that means there is going to be Ft over here. If everything goes well, we can assume that the centripetal force is equal to Ft on the stopper and also equal to Fg, once again, if everything goes well, and that the alligator clip was maintaining the same height with the radius being the same. And that's a key for this experiment. All right, key for this experiment. Of course, the mass is manipulated and changed between trials, but the stopper is kept at the same mass for the version I usually run. So basically, the mv will be the centripetal force, aka Fg, or you can say it's a mass graph, but I'm going to stick with Fg. All right, and the RV actually manipulated is the period of the stopper, or you can also be the speed of the stopper. We usually measure the period instead because that's easier, significantly easier to measure, and then calculate V. So we measure this one, and then calculate V as 2 pi r. Remember, r is fixed over t. Controlled variable already mentioned that the radius will be controlled, and to do that, the reason being, if we change the radius, of course, I will change the speed, and of course the tension within the string, and therefore the Fc, everything changes with it. So to control that, we use the eyeball, the alligator clip height. That is probably the most important thing to control. Okay, that's probably the most important thing to control. Other things you want to control is before you make sure that your rubber stopper is the same one being used. Alright, the string then change between trials, same cylinders, so the friction inside is the same. If everything goes well, of course, no matter what happens, your hand will help to keep it spinning, because especially when the weight, there's a lot of weight, you'll notice that the weight will be so strong, you'll start to pull the rubber stop in and reduce the alligator clips. So your hand will inevitably help spin a little bit, which means increasing the tension just by a tiny bit. That's not because of gravity. That is, once again, going to be a source of error. But the most important control is this one. There should be other controls students should consider when they design an experiment, but there's something students to think about. Of course, like I said, rubber stop mass, okay, same type. The strings material, as well as maybe the alligator clip should be the same one throughout as well, because the alligator clip has mass as well, and that will of course affect the tension. So quite a few things they need to discuss. All right. So the lab handout I usually give, we do measure period, okay, but period is not one spin. We usually spin 20 times, 10, 20 times. Okay, once again, that's something students should control, it should pick. Okay, once again, 20 is going to be harder to maintain without using a lot more of your hand, and of course, if you more hand to exert a force to help the rubber stopper spinning, that will change how much FC there is, because we're assuming, right, we're assuming it is this, but if your hand is helping to spin, it's not going to be equal. It's not going to be equal as our hand jerks the string a little bit, increasing and decreasing tension accordingly. Okay, but you spin 10 or 20 times, and you take the time, 20 times, let's say, divided by 20 to get the actual period. Now, why do we do this? Well, I don't really want to go over that in this video. That's something I do want my students to think about. All right, but if you think about why we don't measure just like 5 times or 6 times, how do we use 20? Okay, if we have time, and not for the fact that your hand has to help more, okay, if not for that effect, I would even say 50, 60, 70, 80, 100 times. Okay, the more times you spin, it's actually the better it gets. All right, the better it gets. But for practical purposes, I usually say 10 to 20 times. All right, but students should stick with 10 or 20, but not both. Somewhere between 15, whatever. But should stick with that. But the more, the better. Why is that? All right, you get the time you measured. Okay, and then you can calculate V as 2 pi r over t. And for this explanation purposes, I am going to graph the relationship between V. Okay, I'm gonna use V as my RV, as my analysis RV, as my example, versus gravitational force, or VC. All right. So if everything goes well, we know FC is equal to mv squared over r. All right. Mass of the stopper, of course, is controlled, and the mass of the stopper. It's somewhat important too. Mass of the stopper, of course, is controlled. R, of course, is also controlled and measured. Both should be measured. All right. So if you graph it out, we'll notice that FC should be proportional to V squared. So if the knock something over here, that's okay. If we graph it out, let me insert some shapes here. If we graph it out, I'll just go down a little bit. If we graph V versus FC, right? That's a function since we're changing FC here. All right, FC is proportional to V squared, okay? Which means V is going to be the square root of what it is, so you'll actually get a graph that goes like this, but definitively increasing. In order to linearize it, of course, you can graph. Okay, you can graph V versus the square root of FC. But more appropriately, you may want to graph instead V squared versus FC. Instead, either one would work, but if you do either of them, your graph will end up being linear. Okay, so I'm just going to graph out V squared and FC, then that graph will be linear. Okay, maybe I should use a line here. All right, that graph will be, well, theoretically should be linear. All right, and the slope, well, if you try to find out what the slope is, well, what is the slope? We can find the slope of the linear one, right? Linearize it. When we find the slope of the linear one, we'll notice that FC, of course, is equal to, well, m over r over v squared. If you don't see it already, okay, we can be a little bit more careful. If we match the equation of a linear function, which is m equal to mx plus b, which students usually learn in like grade 10 math class, you'll notice that since y is indeed I may have gotten it backwards. To rearrange, okay, if you've not seen it yet, well, we're going to erase this first. Wait, why? Oh, I have to use a pen to erase, don't I? Okay, fine. All right, there we go. Okay, so first I am going to rearrange my equation to isolate for v squared. So v squared, okay, v squared is equal to, well, r over m times fc, right? Since my x-axis is my fc, so when I rearrange, my y is v squared, my x is fc, so it follows that my slope should be r over m. All right, y-intercept also should be 0. It's unlikely your slope is going to be 0. Okay, and when fc is not moving, v squared, speed should be 0, right? It's not moving, but due to certain errors that you encounter, you will notice that it won't actually end up being 0. But you'll find that if you graph v squared over fc, the slope, the OneNote is too smart. Slope is equal to r over m. Okay, slope equal to r over m. The similar lab can also be done if you graph period, okay, versus, I should probably do that. You can also do this lab with period as well, okay, depending on which version you want to do. Okay, it works just as well. Okay, if you use t versus fc, of course, once again, using the formula, fc, of course, is mac is equal to m times 4 pi squared r over t squared. Once again, everything up here is controlled. Mass and radius both being controlled. So you notice fc is inversely proportional to 1 over t squared. So that does mean that you will get a reciprocal relationship. So you get a graph that looks like that. Based on our theory, we should be graphing instead. Okay, we should be graphing instead. Of course, you can graph 1 over fc square root of fc. You can graph t versus 1 over square root of fc, but that's not the calculation that may make things a little bit complicated. But the most intuitive one, of course, you would graph t squared over fc, right? You would get, because once again, we're changing the centripetal force. Interesting. What happened there? Okay, so you can analyze accordingly. I am not going to finish analyzing this entire thing, but 1 over t squared over fc. So that one will be linear. I'm freehanding this one. Okay, and the slope in this case, will be, well, let's take a look here. Flipped, so slope would be 1 over m. It will be 1 t squared will be, let me see here, so m 4 pi squared r, right? So 1 over t squared is equal to, I made a mistake, it's 1 over that. 1 over that, there we go. All right, so either version of the lab you can do, and then of course, experimentally we controlled for the mass and we controlled for the radius. You can then compare your theoretical value, okay, to the one you found from the slope. Okay, so you can compare this versus the actual value you measured from your experiment. All right, so that's how you can use a simple lab like this to sort of analyze how things to do a little lab report to verify some values, but also get some information, see how these things connect, and then you can also check how much factors are actually maintained through by comparing your experimental value with the real value. Of course, like I mentioned early on, there's a lot of source of error here, being not just friction in the plastic rod, but your hand has to help, right? And of course, your rubber stopper is not going to spin perfectly horizontal. The string actually, the spinning actually contributes to a little bit of gyroscopic precision, stuff like that. Those things are not accounted for. We're assuming everything's perfectly transmitted through as a perfect frictionless pulley, right? We're assuming Fc equal to Fg. So those assumptions are, of course, not going to be perfectly true, right? So, but this is a nice thing to investigate. Students should realize, of course, as I mentioned, speed should get faster and faster as Fc increase, which of course is more acceleration. It's getting pulled harder, and therefore, in order to maintain a circular motion, okay, without collapsing, you have to move significantly faster. That's also the reason, okay, why your hand has to help to boost the speed a little bit to maintain that circular motion. But okay, to help maintain circular motion, all right, because the air resistance and friction will quickly decrease the speed below the minimum speed required to maintain circular motion, and then the circular motion will fall apart. Okay, so that's why your hand has to help. So that's a circular motion lab, okay, where we I would say pretty straightforward. Actually, quite interesting because this time you'll see two different type of graphs, both the square root and the reciprocal square root function graph here, right? So that is a circular motion lab I do. The second lab I do is the what I call a take a plunge lab. Okay, take a plunge. Mainly, this one is not exactly the greatest lab ever, but it's also quite interesting. I'm looking into things. I'm looking into modify this lab because a lot of things we could investigate. But the basic idea is you have a little stick here. I usually use some old markers that run out of ink. A stick, okay, or something, any mass, some mass here, okay, as we simulate as a diver, and here is like a water tank, all right, and we want to measure how much force does this water actually exert on the diver, all right. Our idea is maybe the force of water is the same for all trials, okay. So we want to measure, see if the force of water is, well, effectively, is it a constant and stuff like that. All right, in this theory, we're going to assume the force of water is constant, but something actually gets pretty interesting. For the trial, for this one, on a small scale, it'll work, but on a larger scale, something actually becomes quite interesting, and that's something I do want to explore further. But, so basically, let's say, all right, to keep things simple. So basically, you leave the diver up a certain height. Now, it's very important to know where you measure the height from. All right, you need to choose a reference height, and we usually choose, most students will choose reference height, which is reasonable, to be the surface of the water. All right, it's height equal to 0, and the height, of course, will be from here to where the pen object is. If you're using a pen or a stick, okay, this is also very interesting because you have to make a decision. Where do you measure the height of the diver from? Is it from the middle, from the top, from the bottom? The instinct, of course, is choose the middle. Okay, because it's center of mass, but you notice the stick is not perfectly cylindrical. Maybe you should give them a strange shape to try out. Okay, I would give them a strange shape if I have time. Okay, but the point is, it doesn't actually matter where it is because what matters is a change in height, unless of course this object is stretchy and changes shape. Where the height you measure from doesn't actually matter. Okay, but let's, for this demonstration purposes, let's just say pick the bottom of the pen. So that's starting height. And then when you drop it, it's going to go a certain depth. So you're going to go a certain depth, D. Okay, and then of course at point D, you'll stop for a moment, then come back up. We're going to manipulate how high the object is dropped, and now we'll see how deep it goes. Now, how does this relate to water? Well, if we assume, okay, we assume energy is conserved. All right, we assume energy is conserved, and all the work done is done by, well, and ignore air resistance. All the work done is done by water. All right, then we can say that the total energy is conserved. So energy initial, okay, plus the work, in this case, the only force doing work here is done by water, should equal to the final mechanical energy. All right. Now, if we choose the height of water to be the surface of water to be 0, okay, then the initial mechanical energy, of course, will just be very easy. It's not moving, so it's going to be mgh plus the work done by water will be the force of water applied for distance d. The final height, of course, will be below the water. Okay, below the water. Okay, actually I should say minus because water will do negative work. Okay, say minus here. Cosine theta, right? Minus d. All right. Oh, same color. Minus force done by water. Final energy, of course, is below. Some students will say, well, maybe the final energy is 0 because it's not moving. It's not at height anymore. That's a simplified model. If we assume final energy is 0, you can solve it that way. But if you want to be more accurate, okay, this would not be quite correct. However, I will not. You know what? I'll give the correct version. Okay, the full version. But if a student decide to call it 0, okay, sure. This leads to some issues, of course. Of course, 0 being, of course, it's not above surface of water anymore, and it's not moving, so the final energy is 0. reasonable. Once again, not quite correct. If we do that, okay, if we do that, then we rearrange for our variables. Remember, this is our RV. So isolate for that one. So you get D is equal to mgh over W, okay, of work done, force of the water, all right, and then of course you're gonna do y equal to mx plus b, and this is my x, this is my y, so the slope is mg or fw. So once again, if you make this assumption, okay, the final mechanical energy is completely zero, okay, then slope is equal to mg over fw, or otherwise known as the weight of the pan over fw. So you can find a force of water, which is going equal to force of gravity divided by the slope. Now, so based on this theory, therefore, if our graph is linear, the force of water will be constant because the slope is constant. Therefore, if linear, then no matter how high you drop it, the force of water will be the same no matter how high you drop it. Okay, then the force of water is constant Fg over slope. Now, what's a problem with it? Okay, what's a problem with it? If you are watching this video, and if you are, it doesn't matter if you're a teacher or a student watching video for some resources, okay, regardless, I would recommend you take a moment and pause this video and think, what is wrong with this analysis? It's workable, but it's not entirely correct. Pause this video and think about what's wrong. And what, okay. Alright, so I'm assuming you paused the video and thought about it a little bit. Alright, now one thing's wrong, of course, is that as you do the experiment more and more, for those with experience, at some point you will stop going any deeper. Okay, stop going any deeper, so you will not be linear, so this analysis cannot be carried out. Yes, but it will actually be linear for quite a bit, then slowly it flattens out. Okay, that does indeed happen. Okay, well, I forgot to mention what your variable. Well, I didn't mention what the variables are. D over H. So you actually be linear, but then slowly flattens out as you get higher and higher and higher. So that is quite an interesting phenomenon that would be interesting to explore. But for the scale of the experiment, it will be linear, so you can still do it. But yes, that would be a good thing. Another thing you may notice, however, is that this assumption right here is incorrect. That's because potential energy doesn't just go up, it also goes down. It's all relative to the reference height, which means the final energy is not actually zero, but instead the final energy, once again we use the conservation of energy plus minus the work done by water. Okay, the final energy should actually be, okay, assume depth is a positive number, should actually be negative mgd, because you actually lost that much energy. That's what should be what it actually is. So to isolate for D, okay, it's very important. Okay, it's not zero, it's actually mgd, negative below the value. Okay, you can use D. If you say D is negative value already, then you use plus here. Okay, but regardless, I'm going to use negative mgd here. Well, I'm treating D as the absolute value of D, I guess. Okay, because I'm assuming you are treating, we're going to graph H, absolute value of H, and absolute value of D, if that's what we're graphing. Okay, which is a raw value. Instead of treating D as a negative number, okay, ignoring direction, basically, you can get this. This is the correct relationship. That means when we factor it out, that D, well, we'll first have to bring them together, which means mgh is actually equal to, why bring it over, plus, so it's actually F of water minus mg times D, right, times D. This is a simple rearrangement. Okay, simple rearrangement, which means D is actually equal to mg over Fw minus mg times h. So slope is actually equal to mg over force of water minus mg. You can still find force of water this way because we're assuming the weight didn't change. Force of water this way. So if the graph is linear, okay, which you'll, for the scale, the experiment does conduct, force of water indeed will be constant. Okay, will indeed be constant. All right. But there's a small caveat, okay, to make this instruction this more clear. Now, depending on how strict I want my students, or I want if you are my students, okay, watching this video, it depends on how strict I've instructed you in class. I may allow one approach nor the other. I may tell you, you may assume the final energy is zero, or I should say, I may ask you to think about what's actually going on. All right. However, if you're just trying to do a quick experiment, exploring how variables work, okay, the top one would work pretty fine. And if you really want students to think about how energy actually conserves, think about physics, think about a physical concept and the various conservation laws of energy, okay, I would recommend students doing it. Now, using this lab, one of the biggest thing about this lab, I'll make a small detour, okay? The lab is interesting at all, but there's some detour about this lab. This is a lab that cannot be done without assistance of technology, okay, without assistance of technology. Oh, this one is weird. No, it's kind of cool actually. Let me use it. Without assistance of technology, because the depths, how deep the object goes, it's going to be very difficult to measure. Okay, so it's recommended student record it with a camera. Okay, with a camera, phone camera, and they put a meter stick, okay, behind with a camera. Then you can slow down the video later on to see how deep it actually goes. There's also a plethora of tracking apps you can find on the internet. So you can make it. There's probably even apps on the app stores for various software devices. Okay, like iPhones or Android, whatever. Okay, it's best for them to actually use a slow motion video to analyzing it. Okay, and if time allows, do multiple trials for each and average it out. Because once again, this is where we little bit. If you cannot eyeball this because everything happens so fast. Okay, so more trials they do and get multiple trials for different depths, it's better to get a more accurate result. But if you have only one, you definitely hopefully have a video footage of it, how deep it goes, and you can use that to take a look. And that's the 2 Unit C lab that tends to do. Okay, one on circular motion or energy. There are other lab ideas. There are other lab instructions and lab analysis techniques for my students and for other teachers. I will post more. Well, but that's for these labs, Unit C Lab Physics 20. This is it. Well, thank you for watching, and I will see you later.